Good morning, students. Uh, so we have finished vibrations, and today we are moving into the next topic, that is mission design. Okay, so with regards to vibrations, still you can ask questions whenever you find a problem where you need a clarification. And also, I'm slowly recording the problems which I gave as a homework for you. So I'm going to put them in YouTube for your ready reference in future. And I'm just uh, compiling all the videos, and I will publish, and I will give you the links. So even I'm going to prepare videos on the questions which you guys have raised. Okay, so that it will give you more clarifications, and it will be you can always keep referring to them till your preparation. So that's what I'm trying to do. Even same thing I will do with mission design as well. So you guys keep ask the questions, even it is silly questions, so that I will understand what kind of difficulties you guys are facing, and then I can able to resolve them. So so with that in mind, today we are going to start a new topic, that is mission design. Also, some people call it as design of mission elements. Okay, so this is basically an engineering design, we call. So the designer plays a very big role in any product development cycle, because he involves in the product development from beginning to end of life cycle of any product. So that's why the designer plays a very key role in any product development. So that means it has a lot of respect. The designer has a lot of respect in engineering, uh, especially in research and development areas. So what are the basically what a designer do, and why it is so important? Okay, so uh, the indirectly, if you consider the role of a designer, initial stages where a product is about to take a shape, so he becomes a creator. Indirectly, in a way we can put it like he becomes a creator in the beginning of any product development. He defines all the key things and shape and everything. Of course, the styling is different from design, but after the styling, uh, the designer plays a major role. So in the beginning he becomes the creator, and the later stages he becomes the evaluator. So he will with the foreseeable conditions he might have designed, and now he will cross check whether that is satisfying or not. Any product, that could be a vehicle, or that could be a even pen which you are writing. So the same kind of principles applicable for any kind of a element which we design. Okay, so the major steps involves in a design process I will write here in a crude way. So this is like major uh, uh, engineering steps. Like, first he will do the kinematic scheme. Okay, so kinematic scheme, the first step, and then he will uh, he will do the analysis of force, and then he will design for for strength or rigidity. So these are the major steps involved in design process. Okay, but the kinematic scheme is nothing but what you will do is you will specify or define the problem and selection of proper kinematic mechanism. Okay, so those are the steps you will do here. So this involves defining the problem statement. Let us say that you have been asked to design a pen. Okay, that is our problem. Okay, first you need to define the problem. So what is the purpose of that product, and how to use that, and all those is the defining a problem. And then you will select the mechanism, isn't it? Because uh, it has to function. So for that you need to select the proper mechanism for that. So here the defining the problem and proper selection of mechanism. This as a I think from uh, mechanical engineering subjects point of view, you will study them as theory of machine. Okay, so as a part of theory of machine, you do these things. So you will select the proper mechanisms for a given problem, and then you will do the kinematic analysis, isn't it? So that is also part of the activity. Okay, so you will do the kinematic analysis of the mechanism. So after that, you do the analysis of force. So for a given operation, what kind of forces are developed, and so like if you are trying to uh, develop a pen, so for pen also, like you should whether you can able to remove the refill or not. For that, what kind of mechanism I have to design. So is it operation? Is it only just a cap type pen, or is it a spring operated kind of a pen? If it is spring operated kind of pen, what kind of elements I have to choose in order to operate? So these are all the things you will do as a problem statement and selection of mechanism and their kinematic analysis. Uh, so uh, because for a given uh, velocity and displacement accelerations, how different elements are moving, are they defined motion is exist between them. So that is what is required, because you will be, I think in the theory of machines you might be studying like degree of freedom. So we will be trying to have a constrained motion. We will be having different elements, we will be connecting them, we will be pairing them, but in the end, whether they are giving a defined motion or not, that is what is important for us. And in all engineering applications, we will be trying to get a degree of freedom 1, so that you will have a defined motion, so you can able to work with them. So in what direction it is moving, and how we can able to control, and all those things can be done. So these are all part of your theory of machine study. Once that is done, then you will go for analysis of force, like when you are holding a pen, what kind of force you will apply, and when you are operating the spring, what kind of force are you are applying. So these are all forces, the force analysis and their effect on the these elements. So that is what we are going to do as a part of mission design here as a designer. Okay, of course, in product development cycle, the designer has to do all these functions on his own. But the difficulty which you arrive in the practical scenario, that is, so these forces, what we are talking, may be unknown force most of the scenarios. And if it is a new product, then absolutely you will not have any idea what kind of level of forces developed and what kind magnitude wise, and even what type of force, okay, load basically. So without that also you should able to develop a product. So that kind of scenarios you will encounter. That is a practical reality. So that is the reason what you do is you execute first this process, and then based on the feedback, then you will again uh, modify them, because you will have many uncertainties, unknowns. And even if you know the force, so when you are designing, so you will be having only mathematical formulations. So for all kind of force scenarios you may not have a mathematical formulations. So in those scenarios what designer does, so he will take the help of empirical relations. That comes maybe because of the lab experiments, or it can be experience with previous designers have experienced with that unknown force for a given system, how it behaves. And those as comes as a rule book, designer rule books. So either you use the mathematical formulations or design a rule book in order to design a component, isn't it? So this is an iterative process. There is nothing like in a one shot you will design a product. So and it is a time taking process. So you will first define them and analyze them, and then you will put that into test. Then based on the test results you will again modify them. So that is the reason the designer role is very important, because he involves from beginning. So where he is going to define the problem and he selects the mechanisms, and then he will based on the test results he will reiterate and he will finish the product. That's the reason he is a key person in any design process. So again there are few more steps which are involved. So this is from a textbook point of view, the way we do the design process here. As a part of mission design we will do this part, okay. So this is basically we are going to do here. So basically again within the design also we call it as designing for strength and designing it for rigidity. So what do you mean by strength and rigidity? It is like if you have taken a component and you are applying a load and it may fail if it is not able to sustain for that force. So that is directly failing. So that is a strength. We call it as design for strength. In some scenarios where it may sustain for your loads strength wise, but our engineering requirement is not about the failure mode. It is about the rigidity. Rigidity means like if you take a shaft you are trying to design for an electric motor, or it might be propeller shaft, uh, kind of scenario where your angle of twist should be limited. Otherwise what is going to happen, the shaft itself will take your energy, and it will not transfer the complete energy from source to receiver side. So we need to minimize the losses. So in order to do that you need to maintain certain rigidity in the component so that you can limit the angle of twist. And not only this, we might have discussed whirling of shafts, where the after a load is applied in the center of a simply supported shaft, we have seen that it may deflect due to dead weight. So that deflection also we will limit, because as we've seen, one of the problem is the vibrational loads it can generate, and other thing is even in operation wise it creates other problems. Okay, so we will be having some acceptable deflection limits. So that is called the designing for rigidity. So there we are not designing it for failure, we are designing it for the deflections or angle of rotation. So all these things will be part of rigidity design. Okay, so In general, the rigidity design is with a high, uh, uh, it requires a higher, indirectly higher strength compared to a strength design. Okay, so what is basically design means here, you will be selecting the proper material and dimensions of the component in order to sustain the given applied loads. So that is what is the design process. So basically you are going to do two things. One is selection of the material and other is finding the proper dimensions. But of course from academic point of view, you will not do in the machine design the selection of material. You will do only the selection of analysis of or finding the dimensions of a component for a given load scenario. So that is the kind of situation we are going to deal. So in real world, you will be asked to select a proper material also for a based on the based on the loading conditions, isn't it? If you are designing a pen, so whether it is a plastic material or metal or something else, okay, or rubber or many things possible. Okay, so those all things you need to decide based on the kind of a loading and operating conditions. But these are all from a systematic way you can do it. But in real world, you will be not only dealing with these things, you will be dealing with many other things as well. Like you will deal with weight targets. Okay, because for a better design, you may ask for a heavy component, or you may design it as heavier. So but in reality, that is from design perspective it is good, but it you may not able to use that because of many reason. If it is automobile, so the weight is play a big role, even not in automobile, in aeroplane industry also, because you have to lift a lot of weight and you have to move with that weight. So your mileage will affect, and many other things will affect, your emissions will affect, and cost of the product will increase, and defects also will increase. So many things happen. So uh, this is a constraint you will have. You may not be in, of course, from textbook perspective you will be able to design the dimensions, but in reality you will be also constrained with weight and cost of the product also you have to keep in mind. So uh, if your product cost increases because of your robust design, then nobody will buy that product. So that is also play a big role, because the finally that product has to be successful. So it happens only with if it is low cost, low weight, and space is also a big constraint you will find, because you will not have space freedom, like packaging we call it as. So like if you even if you look at a vehicle, inside of the vehicle you will have lot of components close by, and within the limited space you need to fit lot of components, like engine compartment. If you see, of course nowadays it is simplified little bit, but still you cannot put a lot of components, because uh, it may hit the engine, or it may hit suspension elements. So many things happen. So you will have a limited space to play with, but that is not considered strength calculation or rigidity calculation, isn't it? So that also play a role, and also the environment in which it is going to operate. Okay, so that like in engine compartment alone, if you consider in nearby engine you cannot keep all kind of materials, because the heat it generates, and it also vibrates. So you cannot keep a component within the engine environment, all the components. So you have to put at a distance with a some kind of a, and also you have to choose a material in such a way that it sustains such kind of environment. Okay, so not only this, you will also uh, define the manufacturing process, isn't it? So the if when you select a material, and also you need to define what kind of manufacturing process you have to use to develop. So one is the whether that material availability is also a constraint. So if you have based on your strength, you say that I'm going to use a particular li of aluminum, so that may not be available in India. So that is also play a role in design. So material selection and uh, and manufacturability. So if whether that is really able, we can able to manufacture in India or outside. If it is so, what kind of cost involved and logistics involved, so many things. So uh, and also you will be applying some kind of heat treatment in order to increase the strength of a component. Okay, so those also, whether they are available or not, all those things you have to consider where before you select. So in addition to this, even though it is designer's role, but styling also play a role. Okay, uh, sometimes the styling may not be uh, helpful for a designer from like here we in especially if we are seeing in automotive, the styling is a different role and designing is a different role. People combine these two terms. Styling is done by like it kind of, they are like artists. So they are the artist people, they do based on the aesthetics. So outside surface, how it look, how it should be, and all those. But from design point of view, it may be having a negative effects. Like if you are designing a if you are uh, giving a styling a profile, that may have impact of uh, uh, like wind noise. It can create a wind noise, or drag, it increases. So CFD effects can happen. Also it sometimes create a problem of uh, heavy weight. So many things, like it can have a negative effects on the vibration. So all these things happens because they don't design from engineering point of view, because they are artists, so they will design from aesthetic point of view. So you need to deal those kind of scenarios also in real world. So that is the reason designer plays a key role. He will be considering the engineering aspects and non-engineering aspects as well. So in order to develop a product. Okay, so this is overall way of look at the designing process. And also we haven't mentioned life expectancy and the market which we are going to operate. All these also play a role for a designer. Like whether you are designing a product of 4 lakhs vehicle or 40 lakhs vehicle or 20 lakhs vehicle, whether your product is going to be sell in particular region or in India, within India also, south or north, or if you are selling it outside. So all these things play a role in your design process. So your role is going to be very critical, and you need to have a understanding of all the subjects indirectly. So that is the reason I think you will be studying the design, thermal, and manufacturing. All these aspects put together is a designer. So the function of a designer is a big role in the product development. I hope this is clear to everyone. So this will motivate you to even take the career in the um, designer roles. So now we will come to the subject theoretical aspects now. So when I'm saying it is we are trying to design for forces, basically loads. Okay, so what kind of loads we are talking here, and we'll be talking basically static loadings, dynamic loadings, and from gate perspective, or as a syllabus point of view, we are going to cover these two aspects, and these are required. And then static loading, dynamic loading, and shock loading or impact loading, and random loadings. So these random loadings are nothing but we cannot define mathematically, we can define from statistical point of view, the loadings. So basically these are the four kind of category of loads you will encounter in any machine. Okay, so the machine element will undergo all these kind of loadings. So but we are going to study extensively from subject from the syllabus point of view, that is static loading and dynamic loading. Okay, what is the main difference between static loading and dynamic loading? If applied load is not changing with respect to time, that we call it as static loading. And if it is changing, dynamic loading. Within the dynamic loading we can also say that cyclic loading and fluctuating loads. So these are a different kind of dynamic loadings which we are going to see it later. So initially we will focus on the static loadings, then we will move to the dynamic loading. So we will be increasing the difficulty of the problem. So so first we will understand the static loadings. So within the static loadings, okay, so we should understand few mathematical aspects of a effect of loading. Okay, so that we are going to understand. This is basically we are going to combine the strength of material and engineering mechanics aspects for the design purpose. So uh, I will assume that you already aware of engineering mechanics concepts and strength of material concepts. So we are going to apply those principles in designing of the elements. Okay, that's how we will be doing it. So even though I assume you know, but I will touch upon the key uh, concepts so that you will we can bring everyone onto the same page and we can move on. And also the different people use the different terminal different notations, so that so we will normalize all those notations also, so that standardization also happens, so we will be able to understand the concepts better. So that's why I will touch upon basic definitions as well, even though you know them very well. So first we'll start with stress. Okay, so the stress is nothing but the resistance to the external load. We are we we know that there are different kind of loads going to act on a your element, and that element has to sustain those loads. So then we will say that that design is safe. Okay, so uh, so how it is going to sustain? So basically whenever you apply an external load onto an element, what it does is it will try to resist that external load because of the intermolecular forces. So that means you will develop equal and opposite resisting force internally, and if that force is reaches to a particular limit, then you will see breakage of the component, but till that time it is trying to resist that. Okay, so this is indirectly resistance to the external load. And how you mathematically define? So So when it is trying to resist, then there will be internal forces developed at every cross section of the member, and that we are trying to mathematically define by like this. That is applied force divided by cross sectional area of the component. That we are calling it as stress developed inside of the component. Okay, so this is the uh, induced stress due to the applied force, external force F, isn't it? So here everybody knows that the all the notations here. So this is the external force and this is the area of cross section of the member, and due to this this is the stress developed. Okay, so this is again based on the kind of loading we will define, we will say what kind of stress is that. If we are applying a tensile load, that means if for a given application of load your length of the component is increasing, that we call it as tensile load. Okay, this is your tensile load understanding. And if your external load is trying to decrease the length of the component, we call them as compressive loads. Okay, so from mathematical point of view, we call this as positive, and this we call it as negative force. Okay, when it is compressing, and and if it is applied load is up acting normal to the cross sectional area, so that we call it as normal stress. Okay, normal tensile stress, normal compressive stress. Okay, so this we'll call, if it is acting in the x-axis direction, x. Okay, so um, if this is again positive is indicating tensile stress, tensile normal stress, and if it is negative, compressive stress. Okay, these things everybody knows, so I don't want to extend further on these basic definitions, because you might have studied them as a part of, or you may study them as a part of strength of materials. Now when you are applying a load, one is the internal stress will be developed, and also it is important how the internal force developed representation look like. For a tensile load, internal force look like this, because it is they are trying to resist the external load. So if I want to represent internal load for a tensile stress, it looks like this, and for a compressive uh, stresses, the internal load looks like this. So this is internal load representation developed inside of the component for a external compressive loads. Okay, this we are calling external loads. So due to this you will develop normal stress. Okay, and also when you are doing when you are applying these uh, tensile or compressive, there is another operation also going on, the change in length. Okay, so in addition to the development of internal load, also it changes the length of the component. So that's why in order to take care of that phenomena, we will define one more term called strain. Okay, what it does is it the change in length, so epsilon, the change in length divided by the original length. So it is going to take care of the dimensional change due to the external load. So this is the amount of internal force developed uh, on a particular cross sectional area, that is that is defined by this term stress, and then what is the dimensional change happening is defined by the strain. But one thing is clear, that these two operations are happening, these two things are happening, like development of internal stress and change of length, both are happening at the same time for a same kind of operation, that is for external load scenario. So that means there should be a relation exist between these two quantities. So that was first initially developed by Hooke's. So that's why Hooke's law we call it as. So what he says that uh, within elastic limit, within elastic limit of the component, the stress is directly proportional to strain. So that is how he defines. Okay, and the proportionality we cannot use in engineering applications. So we will be defining that proportionality with a constant E is equal to epsilon. So this we call it as elastic modulus or Young's modulus. So uh, so this is how it defines Hooke's law. So within the elastic limit, the stress will be directly proportional to the strain, and that proportionality you can remove by introducing the elastic modulus or Young's modulus, because we are talking as elastic limit. So then the next question comes, what is basically the elastic limit? So in order to understand this concept, so we have to do a tensile test, which is a very popular test for understanding the strength of a component. Okay, so this tensile test, again I will not go into the specifics of how we conduct and what kind of, how do we define the test sample and all those. So I will only take the end results of those testings. Okay, so this tensile test, what you do is you will take the sample which you wanted to test. So that sample will be kept in the inside of a universal testing machine, we call it as. So that has some standard shape. Okay, I am writing here as a solid one, but this is not the way you prepare the sample. Okay, of course, to be specific, it looks like something like this. So because you need to hold it, so in order to holding it, you will prepare the sample in a particular fashion, and you will apply the tensile load like this. So you keep on increasing the load, and you will observe the change in length inside of the component. So that for that, what are the changes happening? So that if you are plotting those elements, so it looks like this. So on one side it is, uh, people call it as load versus deflection curve, or load versus deflection curve, or stress versus strain curve. Okay, so whatever it may be, the way you define, because basically you are going to divide it by a constant area. Here you will be defining dividing it by the constant initial length. So that is the reason both are indirectly representing the same quantity. So basically, what we are interested is the behavior, how the material is going to behave. So interesting observations are that initially the uh, material will show proportionality limit. Sorry if I'm drawing it wrongly. Sorry, I will not use this. Okay, so this is what is the what I will do is, if I could able to draw, yeah. Okay, just consider this one. Okay, uh, so this is the stress versus strain, where to a particular limit, this is going to follow a linear relationship between stress and strain or load versus deflection. Okay, so this is called elastic limit E. This is what Hooks was mentioning. So till that this portion, the behavior of the material is that it is proportionally elongates. Also it regains its original shape. It will have a capability to regain its original shape under the removing the external load. If you remove the external load, the material will take its original shape. That is the kind of character it possesses till this point. That we call it as elastic limit. And then we will have yield point. So I will write it as yield strength here. So from design point of view, I will be trying to call them as strengths. Okay, so this is called yield strength. So the yield strength is the a point where after that it is the component is not going to come back 100% anymore. Okay, it will only come back to a certain level. So that is a limiting point which we are calling it as yield point. Okay, till elastic point the component can regain its original shape, but once you go to the yield point, then it cannot come back completely the original shape or dimensions basically. So because for us it is very critical. So that is the reason we will call this as after this it is a plastic zone, before this elastic zone. So um, the once this but we always try to uh, design the components within the elastic zone, because you will have a control on the material behavior. The moment it goes to plastic zone, you will not have any control on the component, because the dimension changes and how much it will regain you don't know, and all those things will play a big role in designing of a component. So that is the reason we always try to limit the components design within the elastic zone. Okay, so in some scenarios, you will also utilize the plastic zone information also, because in the plastic zone, how the behavior is going to happen, like the yield strength is the strength here. After that, the strength of the component reduces little bit, and then it starts increases again. This happens because the internal structure will align to the applied load. Because of that, again the strength of the component will further increases. So this we call it as ultimate point, ultimate strength. Okay, so ultimate strength is the highest strength which a component exists. Okay, but this is a plastic zone. We are into already in the plastic zone, and this is basically this kind of behavior we are talking for a ductile material. That is also very important. Okay, even though there are many kind of materials which we need to design in real world, but from our subject point of view here, we are going to only design metals. Even but in reality, you need to deal with metals and rubber and plastics and composites, many things, plastics, composites. So many things you have to deal within the plastics. Again, thermoset, so many other things. So within the metals, again, we will be only saying them either they are ductile or brittle. So this is a very crude way of uh, classifying them, but for us this is sufficient. from the understanding the subject. So we will say either it is a ductile material or brittle material. So whatever the behavior I'm representing here is a ductile material, where it will have both regions, plastic zone and elastic zone. The ultimate strength will be in the plastic zone, and this is the highest strength of a component. So so this is ultimate strength, and this is the rupture or failure strength. But from design perspective, we don't bother about till this point. Okay, so we'll be either considering the elastic limit or ultimate strength. So uh, people maybe even can go till yield strength also. Okay, they can design. So this is about the ductile materials. So if it is a brittle material, what you will see is the linearly it varies and suddenly it breaks. Okay, so this is the typical behavior of a brittle material. Okay, so the here the difficulty is that the gap between the elastic zone and yield zone are very close, and you cannot maybe distinguish, just like in the case of ductile materials. So that is a region people define proof strength. Okay, so proof limit or proof strength, that is you will draw a parallel line with respect to 0.2% of uh, proof strain. So that we call it as proof strain. So uh, based on that, you will define the yield point. So the elastic and yield will be very close. Even here I have exaggerated. In reality, you may not able to distinguish them, and then suddenly you will see the ultimate strength. Okay. The advantage with the brittle material is that you will have a higher yield point, but problem with the brittle material is that they suddenly break. So you have to choose the material in such a way that in which environment you are going to operate and what kind of machine is that. So the failure of that component, the sudden breakage of that component may not create a big havoc or complete collapse of the machine. Then maybe you can select a brittle material for that kind of scenario. But if it is like a turbine or some kind of a very heavy machinery, and where you don't know where when it is going to fail, sudden breakage happens, then it is a catastrophic design. So in those scenarios, you may not go for a brittle kind of material behavior. So the advantage with the ductile is that even after crossing the yield point, you have a cushion with the elastic strength, and after breakage also, after reaching to elastic strength also, it will not suddenly break, it will yield further. Okay, it will stretch further. So that during that time, at least you can able to recognize the problem, and you can able to rectify the component. So that is the advantage you will find. But here the yield strength will be on the lower side. So that is a another problem. But in addition to this, we also see another observation with respect to ductile and brittle, is that the brittle materials are weak in shear, and ductile materials are weak in tensile loads. So that is also another understanding which we have to keep in mind when we are designing them. Okay, so then people now we understood that tensile uh, stress, and after that strain, and what is the relation exists between them, and what kind of behavior is these materials possess, especially metals within them, ductile and brittle. So yield strength, ultimate strength, and failure strength. So uh, with this understanding, um, we will define one more stress, that is shear stress. So as I already mentioned, So in previously what we have seen is for a external load, we have seen how it is going to develop internal stress on a normal plane, okay, cross section, okay, inside of the component. We have seen what is the kind of internal stress developed, and because of that what kind of stress indirectly it is developed. Normal stress, basically normal to the plane. That is the reason we call it as normal stress. So the here area of cross section we are talking is this one, okay, normal. But in few scenarios where the uh, stress developed because of the transverse load, okay, so that is defined. So it's like a, classic example of a pure shear stress is that if you take a riveted joint, in the riveted joint the rivets will be undergoing a transverse load when you are applying a external load like this, okay. So this is a kind of classic example of shearing. So here the shear happens the cross section which is uh, parallel to the applied load, okay. Previously this was parallel, this was perpendicular to applied load. So this was perpendicular to applied load. On this plane we have calculated what is the normal stress, okay. This is, but now the element, the machine element which is now undergoing transverse load, okay. Under that scenario what kind of stress are developed, so that we are going to see. So that's this we call it as sometimes direct shear, because there is another stress, indirect stress also, shear stress develops, that we will see it later. So this direct shear, uh, shear stress, how it is defined, again the shear stress notation is tau, and that is calculated as the applied load divided by the shear area of cross section, okay. In the previously we have taken the normal area of cross section, but now we have to take the shear cross sectional area, as, okay. So the pure shear is here whatever is developed on the element indirectly, that will be represented, assume that that is developed like this, okay. So this is how the shear has developed, assume that. And uh, basically since the elemental representation of this shear has to satisfy equilibrium condition also, because under this kind of loading, even though internal shear stress is developed, but still system is in equilibrium state, isn't it? So that is satisfied only when you have when you introduce the shear stress on the other planes, then only you can able to see. So this is the correct representation of a pure shear state, okay, we call it as. So similarly for normal stress, the representation looks like, so if we are talking about this plane, so the normal stress developed on that plane is sigma x, and if it is developed on the this plane, the normal stress developed is sigma y. But the tau which we represent, we need not a single, because this is on a transverse plane, so we will define that as xy plane, okay, tau xy, okay, tau xy, like this we will define. Since we are going to see a complete stress state, under that condition you may have normal stress and shear stress together also, combination also. So that is the reason it is sometimes people represent this also with sigma xx is nothing but also can be written as sigma x, also can be written as sigma xx, sigma yy, okay. So if it is sigma xy, it is going to be tau. If it is xxyy, it is normal stress. So that is a kind of another understanding. If it is going away from the plane, it is positive normal stress, okay, that is developed because of the tensile loading. If it is towards the plane, it is developed due to the compressive loading, the same normal stress. So this is the tau xy. So sorry, this representation, I made a mistake here. So this looks like this. Yeah, this is correct, because it has to satisfy the equilibrium state. Similarly, here also, since it has to satisfy equilibrium state, you will represent sigma xx on the other side, sigma yy on the other side. Sorry. So basically, the complete state of stress can be represented in a 3 dimensions. Sigma xx, so tau xy, tau xz, and tau yx, sigma yy, and tau yz, and tau zx, tau zy, and sigma zz. So this is a complete state of stress. We call it as in an element in 3 dimensions. Okay, so this combines maybe you will have normal stress or shear stress. So based on that, you will keep them. So this is about shear stress, but again, just like how we defined for the dimensional change, so here also there is going to be a dimensional change can occur, and that is called the shear strain, comma. Okay, so the change in basically this represents the what is the uh, change you will observe in the element. Sorry. So this is a shear strain. Okay, so when it is applied with a shear load, it is going to change the uh, shape in this fashion. So that is the shear strain.
Sir, could you go to previous slide once?
So again, just like how we defined between the relation between stress and strain, here also there is a relation exists between shear stress and shear strain, and that proportionality can be uh, defined with the constant g. Okay, so this we call it as shear modulus or modulus of rigidity. So rigidity means how stiff for a dimensional change. Okay, so that is the meaning. So the units are for stress, and even these constants are same, that is Newton per meter square, because force divided by cross sectional area. And but in reality, the change in cross sectional area or length and those things won't be in meters, it will be in mms. You don't expect a meter change for a given load in that kind of materials we don't deal also. So that's the reason you encounter this as newton per mm square most of the times. So that's why this is a pascal also we call it as. Okay, so this Newton per mm square also can be written as megapascals. So, because in reality, you will see the changes in mm's, not in meters. So, this is the kind of notation we use. And if mega and gigapascals, giga means nothing but 10 to the power of 9. Megapascals, I think these things everybody knows, but still I am just giving clarity. 10 power 6 pascals. Uh, then is there any relation exists between the shear strain and uh, normal stress? Sorry, shear stress and normal stress? Yes, there is a relation exist. These modulus especially. So that what is the relation between these modulus of velocity? That relation is E is equal to 2G into 1 plus mu. Because in reality, you would do only the tensile test. You don't do the shear stress because the equipment you don't you need different kind of equipment arrangements, and which we don't which not all the people may able to maintain use them. So that is the reason. So the tensile test is very easy, or it is available everywhere. So that is the reason you can able to find easily E value from tensile test. Once you know E, if I have a relation for E with respect to, so for G with respect to E, then I can able to use that for calculating the G. Otherwise, I need to have a again separate test set up for identifying the G. So which is not a common practice, which is not even feasible, not economical. And that is the reason. So people develop use this relation to calculate G. Okay, they don't depend on the testing results. For directly getting testing results for G, they use E for calculating the G. So when you are defining this, there is a new term came that is called Poisson's ratio. So the how what is this basically? The Poisson's ratio is so the lateral strain divided by longitudinal strain. Okay, so basically I here longitudinal strain. So the what is mean by longitudinal and lateral strain? If you have applied a load in the length direction, assume, and whatever is the change happening in the length direction, that change if you say delta L, so this is a lateral change, and the strain in that direction with rest, so that is a lateral longitudinal strain, delta L we call it as. But at the same time, there would be a change in the uh, lateral side, that is on the, if you say this is x-axis side, and on the y-axis side also there will be some change, isn't it, in the component. So how do you factor that? How to mathematically take into picture? So that's what we are trying to do with the uh, Poisson's ratio. So your length has increased on the applied load direction, that is longitudinal direction, but also the diameter might have changed. Of course, if it is positive on this side, definitely it will be on the negative on this side. So to in order to uh, take out this negativity, we will introduce minus sign here. Okay, so the dimensional change on the lateral side here is, if it is a shaft, assume, so the delta D change divided by the D will give you the uh, lateral strain. Okay, epsilon T. So basically the Poisson's ratio, which combines these two things, the lateral strain divided by the longitudinal strain. So that is what is given and used here. So once you know E from universal testing machine, then I can able to calculate G for um, calculating the shear modulus or modulus of rigidity. Is this clear to everyone?
Yes.
So what I will do is we will take a break. Uh, I hope all these things you already know. That's the reason I am not I am not gone into the each item very detailed way. I am going on a surface level and I am trying to introduce my notations to you. That is what basically I am trying to do here. Okay, so that is the reason I am just telling you all the things on a surface level, but we will try to get the understandings of these quantities one by one with the problems. So because you might have studied them in detail in the either in strength of materials or in other subjects. So that's the reason we will cover them on surface level, because our main focus is not on these stresses, but using these stresses how to extract the dimensions for the component for a given load conditions. So we will focus more on that side rather on these formulations. Okay, so we will then discuss those points after the break. We will take a break of half an hour. So we'll come back and we will start it again, maybe around 12. So we'll take till 12 the break, and then we'll continue. Meantime, if you have any doubts, you can clarify with me.